This is to show why the dot product, which looks like this, A dotted with B, has the definitions that it does. The magnitude of A times the magnitude of B times the cosine of the included angle when the vectors are tail to tail, which also equals the product of the component parts. All right, so it's a lot of algebra, really, and using basic definitions, but it's a lot longer than what really we could do in class. So a couple things to start off with. If I add two vectors, and knowing that, so A is going to have the x component and the y component, and B has the x component and a y component. So I'm going to call them this way. That when I add the two vectors, what you end up with is, remember, you add their component parts. So A of x, B of x, and then A of y plus B of y. So you're adding the x components of the A and B vector and the y components of the A and B vector. Also, when you find the magnitude of their sum, that it's, and I'm keeping it squared so we don't have any square roots going on, it's your Pythagorean theorem. So it's A of x plus B of x squared plus A of y plus B of y squared. If I just find the magnitude of A, that's going to be A of x squared plus A of y squared, and correspondingly the magnitude of B squared is B of x squared plus B of y squared. So these are just sort of some, general underlying features that we're going to use throughout this proof, and it's stuff that we should already be aware of. So finding the magnitude is just your Pythagorean theorem, the x component squared plus the y component squared. Okay, so let's take a look at what these vectors really look like. So if you put them tail to tail, here is vector A, here is vector B, and we know that through vector addition I can add A, translate it out here, or I could translate B out here, either way, so that the resultant vector goes right down the middle of this parallelogram. So here is A plus B. All right, and we know that the vector between A and B, when it is tail to tail, is right here, which of course, when you guys have done it, we know then that finding, we've had to use the law of cosines, and we have used this up here, which is 180 minus theta, this angle up here, because those are the inside, consecutive inside interior angles, which are supplementary. Okay, so that's our basic picture that we're going to start with, and we're trying to find out why the dot product is what it is. Okay, so we start off with our A plus B, our magnitude of the sum of the two vectors, and in the past what we did was the law of cosines. So we knew that this equaled A, magnitude of A plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B times cosine 180 minus theta. And that's how in the past we found the magnitude of A plus B. We had to use this other angle. So now we're going to do a little bit of geometry. Actually, you guys had this in the first semester. Remember, cosine 180 minus theta, if I used one of your trig identities and expanded that, cosine 180 cosine theta minus sine 180 sine theta, would actually give you that this equals minus cosine theta. Okay, so we're going to need that identity. So we're going to rewrite what we just did. We're going to substitute this here with minus cosine theta, and we're then going to isolate. So we have here a plus b squared minus your magnitude of a squared minus the magnitude of b squared, all divided by -2 times a magnitude of b. That equals minus cosine theta. The negatives are not really appreciated here, so we are going to multiply both sides by -1. So that will make this positive, and all I need to do is distribute it downstairs, because otherwise you'd be multiplying by just 1 instead of just -1. Okay, so here we go. Now from here on out, it's really just going to be an expansion of what it means to find the magnitude using what we derived up above, and then cancel things out. So a plus b, the magnitude of a plus b squared is actually ax plus bx squared plus ay plus by squared. So that's replacing the magnitude of the sum squared. Then we are going to subtract the magnitude of a squared, which is ax squared plus ay squared, and then we're going to subtract bx squared plus by squared, and remember that is all divided by 2 times the magnitude of a times the magnitude of b, and all of that, remember, equals cosine theta. Okay. Now what we have to do is we are going to FOIL out, because you have ax plus bx squared. So when you FOIL that out, you get ax squared, first term squared, and I'm going to do it out of order, the last term squared, plus 2ax bx, so that's the first term FOILed out. Then the second term will be ay squared plus by squared plus 2ay by, and then we're going to distribute our negatives down here. So then we have minus ax squared minus ay squared minus bx squared minus by squared. Remember, this all equals cosine theta, and remember that it has all been divided by 2 magnitude of a, magnitude of b. Okie dokie, now comes the fun part. So this cancels with this cancels with this, and ay squared cancels with that, by squared cancels with this, and lo and behold, you have 2ax bx plus 2ay by. So I can factor out a 2, and by, and this is all over 2 magnitude of a magnitude of b equals cosine theta, and then lo and behold, those 2's cancel, and voila, you get the product of the x's plus the product of the y values equals the magnitude of a times the magnitude of b times the cosine of the included angle, right? Because remember, theta up here is the angle between a and b, tail to tail, and we define that to be the dot product. Ta-da! Pretty Sweet, right? And it's really just algebra.